In finance, engineers face a strict compromise: build highly accurate numerical models operating as black boxes, or output human-readable text failing tight mathematical tolerances. Attempting to bypass this by feeding raw, unannotated time series data directly into a standard large language model yields poor results. Without contextual translation, standard LLMs lack the inherent structure to process raw numerical sequences effectively on a zero-shot basis. To force LLMs to process this data, researchers have developed specialized time series variants. These models physically modify the LLM's internal architecture, actively reprogramming the embedding space to prioritize numerical sequences over vocabulary. That architectural overrate solves the numerical processing problem, but it creates another. By replacing the semantic word embeddings with numerical tokens, the model loses its native ability to generate logical, natural language explanations. The interpretability is destroyed. A 2026 paper presented at ICLR addresses this exact engineering bottleneck with a new architecture called Verbalized Technical Analysis, or VTA. VTA avoids the embedding overwrite problem entirely. Instead of forcing one system to do both tasks poorly, the framework is decoupled into two concurrent aligned branches, one dedicated to language reasoning and a separate latent backbone dedicated exclusively to forecasting. By isolating the mathematical optimization from the linguistic generation, the model can maximize predictive accuracy in its forecasting branch, while maintaining perfect syntactic logic in its reasoning branch. The first half of this architecture is the time series reasoning module. Training this module presents an immediate cold start challenge. There is no massive pre-existing dataset of perfect human-verified financial logic mapped to technical indicators. To bypass the need for human data, the system utilizes a deterministic input phase. Raw price data, labeled here as X, routes through a textual annotator. This component mathematically converts the numerical sequence into hard text values, extracting known variables like simple moving averages, MACD lines, and relative strength indices. These explicitly defined text indicators act as prompts for the language module. The LLM processes the annotated indicators and generates two distinct outputs: a step-by-step textual reasoning chain analyzing the data, and an initial numerical prediction for the next sequence in the time series. Because there is no human baseline to measure the reasoning text against, VTA relies on a multi-stage reinforcement learning pipeline to optimize the module's logic. The mechanism driving this optimization is a custom reward function known as Time Series Group Relative Policy Optimization, or Time GRPO. This equation defines the reward signal. Time GRPO calculates the inverse mean squared error of the model's numerical sequence prediction against the actual historical ground truth data. The smaller the error in the numerical forecast, the higher the reward sent back to the language model. By linking the reward signal strictly to the mathematical accuracy of the numerical output, the LLM is forced to discard flawed technical analysis and actively develop text reasoning that leads to mathematically valid predictions. The second half of the VTA architecture is the latent forecasting module. This is the heavy-duty backbone engineered specifically for high-dimensional, low-level numerical pattern recognition. The primary engineering hurdle here is translation. The numerical forecaster must be forced to analyze raw data through the same semantic lens developed by the reasoning module, without reading the text itself. The data ingestion begins by establishing two distinct inputs. The raw time series data is converted into projected time tokens. Simultaneously, the system isolates the principal word embeddings from the language model. Both of these streams are fed into a cross-attention matrix. The cross-attention matrix forces the numerical time tokens to align directly with the principal text embeddings. The resulting output is a merged cross-modal token that moves forward into the subsequent transformer blocks. Generating a single aligned token is insufficient for deep neural networks. The semantic alignment must be maintained at every single layer as the data is processed. To prevent the text and time branches from drifting apart, an L1 feature regularization loss is applied after every transformer module. This physically tethers the numerical representations to the text representations, enforcing continuous synchronization at depth. Because of this strict layer-by-layer cross-modal alignment, the mathematical forecaster evaluates numerical volatility using the exact same semantic parameters that the language module uses to write the technical analysis. The final phase of the architecture is joint conditional training. This process binds the independent language and forecasting branches into a single cohesive output mechanism. The system extracts specific reasoning attributes, represented here as the variable C, directly from the generated text of the reasoning module. These attributes include defined constraints, like predicted maximums, minimums, and statistical means. The numerical trajectory calculated by the latent forecaster is then explicitly filtered through these textual attributes. The final numerical output is bounded and shaped by the language model's logic. To maintain robustness, the model is trained concurrently. It optimizes for the condition where text attributes are applied and an unconditional state where they are withheld. A probabilistic equation merges these dual paths to output the final price trajectory y. This joint conditioning ensures the numerical output remains strictly anchored to the textual analysis. The sequence prediction is a direct result of the generated language. This table compares the mean squared error and mean absolute error across 14 different baseline architectures, tracking United States, Chinese, and European market datasets. The VTA framework yields the lowest error rates across all tracked indices, outperforming both traditional time series models and specialized time series LLMs. But high accuracy poses an operational question. How can we be certain the textual reasoning is actually dictating the forecast, rather than the model generating an accurate prediction and simply writing a convincing post hoc justification? To verify causality, researchers conducted an ablation study, specifically targeting the integrity of the language module. This chart maps the results of injecting adversarial noise directly into the textual reasoning indicators. As the values of the textual inputs are corrupted, the mean squared error of the numerical forecasting module immediately spikes. The numerical accuracy degrades in direct proportion to the corruption of the text. This proves the latent forecaster is actively dependent on the linguistic logic to function. The text is the cause, not the byproduct. Measuring isolated prediction errors verifies the math, but applied quantitative finance requires evaluating how those predictions behave when capital is deployed. To test this, the VTA framework was used to drive a Markowitz portfolio optimization over a 10-day forecasting window. The portfolio utilized the model's daily predictions to execute strict rebalancing protocols based on expected returns and covariance. The objective was standard: maximize the percentage of returns while aggressively minimizing daily volatility and maximum portfolio drawdowns. This chart compares the resulting Sharpe ratios, the core metric for risk-adjusted performance. While foundational models hover near a 1.5 ratio, the portfolio directed by the VTA framework executes the most efficient risk allocation, yielding a top-line Sharpe ratio of 1.719. By utilizing rigorous cross-modal embeddings and tying reinforcement learning strictly to historical ground truth, the VTA framework forces language models to adhere to hard math. It provides concrete evidence that in highly complex financial modeling, numerical accuracy and full interpretability can be achieved simultaneously.